Combinations, section 11.3. Now in this section, this is going to be somewhat different from permutations, section 11.2, where permutations are about arrangement in ordered sets, but combinations are arrangements where order is not important. Another way to look at combinations is the various ways a group of items can be arranged in unordered sets. So a combination of which items occur when the items are selected from the same group, no item is used more than once, the order of the items makes no difference. So let's look at those three bullets again. A combination of items occur when the items are selected from the same group. No item is used more than once, and the order of the items makes no difference. So the next example, we're going to determine whether the situation that we're going to have here, is it a permutation or is it a combination? For each of the following problems, explain if the problem is one involving permutations or combinations. 6 students are running for student government president, vice president, and treasurer. The student with the greatest number of votes becomes the president. The second biggest vote getter becomes vice president, and the student who gets the third largest number of votes will be the student government treasurer. How many different outcomes are possible for these three positions? So what we want to, as we look at this, is this a permutation or is this a combination? Because remember, permutation says no item is used more than once, and then the order of arrangements make a difference. So whereas with combination, the arrangements of order are not important. So this one has an arrangement. So this type of situation where order matters is about permutations. It says students are choosing 3 student government officers from 6 candidates. The order in which the officers are chosen makes a difference because each of the offices, president, vice president, treasurer, is different. So order does matter. So this is what we would call a problem type of permutation. Next example. 6 people are on the volunteer board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people on the board of supervisors? So is this where this type of problem will be where no item is used more than once, or we have here the items are selected from the same group? And we notice we have this same group of 6 people. So this would be a combination. And let's go back. A 3-person committee is to be formed from the 6-person board of supervisors. The order in which the 3 people are selected does not matter because they are not filling different roles on the committee. Because order makes no difference, this is a problem involving combinations. The third example. Baskin-Robbins offers 31 different flavors of ice cream. One of their items is a bowl consisting of 3 scoops of ice cream, each a different flavor. How many such bowls are possible? So is this a combinations question or is this a permutations question? The items are combination. Remember, the items are selected from the same group. The order of the items makes no difference. So we have here a 3-scoop bowl of 3 different flavors is to be formed from Baskin-Robbins' 31 flavors. The order in which the 3 scoops of ice cream are put into the bowl is irrelevant. A bowl with chocolate, vanilla, and strawberry is exactly the same as a bowl with vanilla, strawberry, and chocolate. Different orderings do not change things, and so this problem is combinations. So with this, it's going to take us into the formula for combinations of n things taken at r times. The number of possible combinations if r items are taken from n items is, so we see our combination of n things taken at r times, where we have is equal to n factorial all over, in parentheses, n minus r factorial times r factorial. So let's do an example. While studying abroad one semester, Tran is required to visit 10 different cities. He plans to visit 3 of the 10 over a long weekend. How many different ways can he choose the 3 to visit? Assume the distance is not a factor. Okay, so we want to look at what are we going to call n and r? So here's our solution. The problem doesn't say anything about the order in which they'll be visited, so this is a combination problem. So we have n items, okay, or n things taken, 10 things taken 3 at a time. Let me say this again. We have 10 things taken 3 at a time, okay? So 10 different cities, 3 at a time. So here's our combination, 10 factorial all over 10 minus 3, the quantity of 10 minus 3 factorial times 3 factorial. So we have 10 factorial over 7 factorial times 3 factorial. And you see the work there. So how many different ways can he choose the 3 to visit? We have 120 different ways.